This is the revision video for the Unit 3 Mechanics topic of power. As far as the specification is concerned, it simply says that candidates are expected to understand and use the concept of power. We need to know that power is simply the rate of doing work, that units of power can be expressed either as joules per second or as watts. And the key result is that for a force of F newtons acting on a body in the same direction as the velocity of the body, then the power is given by the product of the force and the velocity. Now, a particularly important application of this result is that if we have a vehicle whose engine is working at a rate of p watts, then the driving force or the tractive force, d newtons, is given by d equals p over v. That's simply a rearrangement of the result p equals dv. If the force that we're dealing with and the velocity are in different directions, then we need to use a scalar product to find the rate of doing work, the power output of the force. And we'll see use of that in the course of the work on vectors later in the module. So let's move on to some examples. The first one comes from the WJCE paper of 2010. We have a car of mass 900 kilograms can produce a maximum power of 45 kilowatts. The car experiences a constant resistance to motion of magnitude 1800 newtons. We've got to calculate the maximum speed of the car while it's travelling on the horizontal road to begin with. So we'll start by drawing a diagram. So there's our car. We've got the weight of the car, we've got the normal reaction of the ground on the car, which of course would act through the 4 different wheels, but we're showing it just as a single force at the moment. We've got the driving force, and we have the resistive force of 1800 newtons. Now there may be some acceleration, and we know to begin with that, well, we're trying to find out the maximum speed of the car. Now, if the car is travelling at its maximum speed, then that means the engine must be working at its maximum power, and there will be no acceleration, because the speed is the maximum. So therefore, dv by dt, in other words, the acceleration, will be 0. Well, we know that P is d times v, so we've got the driving force of the car times by u must be 45,000. Remember, we must use SI units, so 45 kilowatts becomes 45,000 watts. So we have 45,000 equals D times U. But we also, so D must be 45,000 over U. But Newton's second law, applied to the right, tells me that D minus 1800 must equal 900 times the acceleration. So we've got d minus 1800 must equal 900, must equal 0. So d must be 1800. So we've got 45,000 divided by u must be 1800. In other words, we have u is 25 meters per second. Now in the second part of the question, we have the car travelling up a slope inclined at an angle of 4 degrees to the horizontal. Assuming that the maximum power is still employed, we have to calculate, correct to 2 decimal places, the acceleration of the car at the instant when its speed is 15 meters per second. So again, we need to draw a diagram. So we've got the car going up the slope, we have the weight, we have the driving force, we have the reaction, and we have the resistive force. Acceleration is what we are trying to find, and we know the speed of the car at the moment is 20 meters per second. So, first of all, we know that P must equal D times V. So we've got 45,000 divided by 15 is P divided by V, which is D. So the driving force must be 3,000 newtons. So we can now apply Newton's second law up the slope, since the acceleration is up the slope. So we have D minus 900g sine 4, that's the component of the weight acting down the plane, 900g sine 4, minus the 1800 must equal the mass of 900 times by A. D is 3000, 900g sine 4 we can work out on the calculator, 1800 we can work out on the calculator, so the left hand side simplifies to 584.7 equals 900A, so we've got A is 0.65 meters per second squared. Now we're asked to work out the work done as the car travels a distance of 800 meters up the slope, and we're simply asked to calculate the work done against the resistance, and the work done against the resistance is simply going to be the work done against the 1800 newtons, so that's simply going to be 1800 times by 800, which is 1,440,000 joules. So let's just have a think about the assumptions that we've made in this answering this question. We've treated the car as a particle, and an improved model would certainly have the reactions acting through each of the 4 tyres. We've assumed constant resistance. This is unlikely since air resistance would be a major factor, and air resistance certainly varies with speed. Moving on to another example, this time from the 2013 paper. We have a car of mass 1500 kilograms is towing a trailer of mass 500 kilograms by means of a rigid tow bar up a slope inclined at angle alpha to the horizontal, where sine alpha is 1/14. We're told the resistance to the motion of the car is 170 newtons and the resistance on the trailer is 30 newtons. The car's engine is working at a constant rate of 60 kilowatts, and that the car and the trailer are currently moving at a speed of 20 meters per second. So let's start by drawing our diagram. So we've got the car and the trailer going up the hill. We've got the weight of the car, weight of the trailer. We have a resistive force of 170 newtons on the car and 30 newtons on the trailer. We've got a driving force on the car. We've got the car and the trailer going up the hill at 20 meters per second. There's going to be an acceleration up the hill as well. And to complete our diagram, we've got the reaction of the ground on the car and on the trailer. So, we know that P must equal D times V. Rearranging that gives us D equals P over V. So the tractive force acting on the car is going to be 60,000. That's the power of the engine in watts, divided by 20, which is 3,000 newtons. So we can now use Newton's second law up the slope. And we're going to apply Newton's second law to the whole system. So we've got D up the slope, we've got the 170 newtons resistance on the car, the 30 newtons resistance on the trailer. We've got 1500g sine alpha is the component of the weight acting down the slope. That's the component of the weight of the car acting down the slope. And we've also got 500g sine alpha, which is the component of the weight of the trailer acting down the slope. So there's my resultant force, must equal the total mass, which is 2,000 kilograms, times by the acceleration. So we've got 3,000, take away 200, that's the two combined resistances. 1,500 times 9.8 times sine alpha, which is 1/14, gives me 1,050. 500g sine alpha, similarly, gives me 350. Must equal 2,000 alpha. So we've got 1,400 equals 2,000 times the acceleration. So we've got the acceleration is 0.7 meters per second squared. Final part of the question, we've got to determine the tension in the tow bar. Now if we're going to do that, we've either got to consider the car alone or the trailer alone. It's slightly easier to consider the trailer alone. Now as far as the forces acting on the trailer are concerned, we've got the weight of the trailer, we've got the resistance to the motion of the trailer, and the trailer is being pulled up the slope by the tension in the tow bar. Now again, we can apply Newton's second law to the trailer alone. So applying Newton's second law up the slope for the trailer, we've got T minus 30 minus 500g sine alpha must equal the mass of the trailer, which is 500, times by the acceleration. So we've got T minus 30 minus 350 must equal 500 times A, but we know that A is 0.7. So we're ending up with T must be 730 newtons. A more realistic model would be one where the resistance depends on the speed. And here's an example where we've got precisely that. We've got a car of mass 1,200 kilograms, moves against the resistance which is proportional to its speed. At a power output of 72 kilowatts, it has a maximum speed of 108 kilometers per hour on level ground. If the car is working at a constant rate of 18 kilowatts while travelling down a long slope inclined at sine to the minus 1 of 1/40th to the horizontal, we have to find the acceleration of the car at the instant when its speed is 54 kilometers per hour, and we have to find the maximum speed of the car as it goes down this slope if it's working at a rate of 18 kilowatts. Now the major thing we don't know at the moment is how exactly the resistance is related to the speed. But we have got enough information to work that out if we just look at the first paragraph of the question and we concentrate on what is happening whilst the car is travelling on horizontal ground, travelling at its maximum speed. So let's start by putting all of the information onto our diagram. So we need to put the forces, the speed, the acceleration, all onto the diagram. Okay, so we've got the weight, we've got the normal reaction, we've got the driving force, and we've got the air resistance, which is proportional to speed. So the air resistance, or the resisting term, is K times V. We've got the speed of the car as v meters per second, and we've got the acceleration of the car, all shown on the diagram. Now the first thing we need to be careful about is the speed has been given in kilometers per hour. We need to make sure that we're using SI units. So 108 kilometers per hour is the same thing as 108 times 1,000 meters in 60 times 60 seconds. So with 108 kilometers per hour comes out to be 30 meters per second. On the horizontal road, we have no acceleration when v equals 30 and the engine is working at 72 kilowatts. So Newton's second law is going to tell me that the driving force minus kV must equal 1200 times 0. In other words, we've got the driving force of 72,000, that's the power, divided by 30, that's the speed in meters per second. Take away k times 30 must equal 0. So we've got 72,000 divided by 900 must equal k, which gives me k equals 80. So we now know that the resistive force is 80 times the speed. So now looking at part A of the question, we clearly need to begin with a new diagram. So we've got the car going down the slope, we've got the weight, the reaction, we've got the resistive force of 80 times the speed, we've got the driving force going down the slope, we've got the speed down the slope, and we've got the acceleration. So if we apply Newton's second law down the slope, we've got d plus the component of the weight down the slope, which is 1200 g sine alpha, minus 80v must equal the mass of the car, 1200 times by a. We know the car is working at 18 kilowatts, so the driving force must be 18,000 divided by v, where v is the speed of the car in meters per second. So the equation we've just got for Newton's second law can be rewritten as 18,000 divided by v plus 294 minus 80v equals 1200a. And this equation will be absolutely the key equation as we try and answer both part A and part B. Looking at part A to begin with, we've got a speed of 54 kilometers per hour. So 54 kilometers per hour is the same thing as 54 times 1,000, which is 54,000 meters in 3,600 seconds. So that is a speed of 15 meters per second. So the equation becomes 1200 plus 294 minus 1200 equals 1200a. So a is simply 294 divided by 1200, which is 0.245 meters per second squared. Moving on to part B, the diagram and all the working up to the highlighted equation is exactly the same as in part A. This time we have the car going down the slope at its maximum speed. So if it's travelling at its maximum speed, the acceleration must be 0. So the equation becomes 1800 over v plus 294 minus 80v equals 0. Multiply up by v, we've got minus 80v squared plus 294v plus 1800 must equal 0, which is a quadratic equation. And if we solve that quadratic equation, we will find that the positive solution is v equals 16.95 meters per second. And this is our maximum speed for the car as it goes down the slope. And 16.95 meters per second converts to a speed of 61 kilometers per hour.